Hello, in today's video we're going to be talking about the Bohr model of the hydrogen atom. Now we've talked about this previously in a couple videos ago, however we're going to go into more detail in today's video and we're going to be able to predict different jumps of an electron, either moving towards the nucleus or moving away from the nucleus. Now this is our pictorial representation of what the Bohr model of the hydrogen atom looks like. We have our nucleus surrounded by concentric circles that are called orbits. These are just like the orbits of the planets surrounding the sun. So Earth follows in a circular orbit, semicircular orbit. Here we're going to have the same type of thing. Now we're going to be using the hydrogen atom because the hydrogen atom only has one proton and one electron. It makes the math a whole lot simpler. We can use the same type of calculations for any hydrogen-like system. So if we went on to helium and we stripped away one of the electrons, helium would have a very similar nucleus with only one electron. So the second that we start inputting in more electrons than just one, this model breaks down. So we'll be dealing with hydrogen for the rest of this part of the class. So let's say that we have these concentric circles. We can label these with just a number, a whole number. The first circle is going to be n equals 1. The second circle is going to be n equals 2, and so on. n equals 3, n equals 4, n equals 5. Oh, 5. Now let's say our electron is in the 5th orbit. So here is our electron over here. It's circling around the nucleus. We know that this isn't really how electrons behave, but this model still does predict a lot about light, so we're going to still use it. We're going to talk about it. Now, let's say that this electron ends up giving off energy to the surrounding. So if an electron in a hydrogen atom gives off energy, it means that that electron is now going to move closer to the nucleus. Okay, so this electron, let's say that it gave off enough energy to drop down to the n equals 3 state. Now, this is going to give off energy in the form of some sort of wave, some sort of light. So this is going to be E, energy of a photon is going to be coming off of this. It's going to be a packet of energy. Now you'll notice that I didn't drop down to n equals 3.5. That's because there is no n equals 3.5. In the hydrogen atom of the Bohr model of the hydrogen atom, the rings have to be whole number increments. And this is where our term quantum comes from. That means that our energies are going to be quantized. There's a certain or very specific energy that can come off of an electron dropping or moving closer to the nucleus, and there's a certain or very specific energy that's required for an electron to jump to the next shell further away from the nucleus. So these jumps can only occur in whole number increments. This was a change of 2. It could have been a change of 3 or a change of 4 or a change of 1, but they have to be whole number increments. So we're going to be moving up and down, closer to the nucleus, farther away from the nucleus, and calculating the energy of that change. Now I'm going to give you a different view of this. Let's say we have the energy in a plot like this. We're going to have n equals 1 at the bottom. N equals 2 has higher in energy. N equals 3 is a little bit higher than that. N equals 4 is still higher. And n equals 5. In this case would be the highest. This is the furthest ring out that I drew. So let's say we have an electron. Our first electron is going to be in the n equals 5 state. Now, when electrons drop to 3 of these specific whole number increments, the n equals 3, n equals 2, and n equals 1, we have a given name for that transition. So let's say our electron's in n equals 5, and it drops all the way down to n equals 1. Anytime an electron drops down to the n equals 1 state, this is called the Lyman series. So this is called the Lyman series. This outputs ultraviolet light. Ultraviolet. And this is when n final is going to be equal to 1. Okay, so anytime, if it was in n equals 4 and it dropped down to n equals 1, that would still be a Lyman series transition because the final state is n equals 1. Let's say we have a second electron, different hydrogen atom, and it started out in n equals 5, but it dropped down to the n equals 2 state. N equals 2 is another special transition. This is called the Balmer series. Balmer series. It is the visible spectrum. Visible spectrum. This is all of our colors that we can see with our eyes. Reds, blues, greens, purples, yellows, all of those colors happen when an electron drops down to the n equals 2 state. So n final is going to be 2. And the last named state that we're going to be talking about, let's say we have a third hydrogen atom, starts in n equals 5, and it drops down to n equals 3. This is called the Paschen series. Paschen series. This is the infrared light. Infrared. So anytime you have an electron that's above n equals 3 and it drops down to the n equals 3 state, that is called the Paschen series, and that will have n final equals 3. So not only do we have these transitions going on, but we have special named transitions. We've all heard of ultraviolet light. This is the light that the sun produces that burns your skin. It's very bad for your skin. We've all seen visible light, or the majority of us have seen visible light, where we see the different colors. That comes from n equals 2, n final equals 2. And infrared light, this you haven't seen, you have to have special goggles to see these. This is where you have n final equals 3, and that's called the Paschen series. Now, how in the world, what equation do we use in order to identify the energy change from going from the n equals 5 state to the n equals 1 state? Well, it's an equation that we've not seen before. So the change in energy of an electron going from any of these states is going to be equal to minus RHC, these are all constants, times 1 over n final squared minus 1 over n initial squared, where n initial is the initial starting orbit, and final is your final orbit. Let's talk about these constants. R is called the Rydberg constant. Rydberg constant. It has a value of 1.09678 times 10 to the 6th inverse meters. This is just a new constant that we've never seen, but remember our gas constants all have the constant R, all have the connotation of R, so this gets a little tricky. This R is the Rydberg constant, and it has inverse meters. H is Planck's constant, which we've all seen before. This is the 6.626 times 10 to the negative 34th joule seconds. And then C is the speed of light. And that has units of 3.00 times 10 to the 8th meters per second. If you were to multiply all three of these constants together, the units would cancel out in such a way that we would end up with joules. That's where our energy term comes from. There are no units for each of these, so we would have a joule times no unit, which gives you a joule, which is an energy term. So tomorrow in class, we're going to be dealing with this equation a lot. We're going to be doing a lot of different transitions. We're going to be doing certain transitions for each of these three different named transitions, the Lyman series, the Balmer series, and the Paschen series, and we'll be using each of these constants. Now, there's no reason to memorize the constants. I give you all of them on the exam. However, you should be aware that these constants exist. So with that, I want to let you go. I will see you all in class tomorrow, and we'll be working with the Bohr model of the hydrogen atom almost all day. Have a great night.